Hello, in this video we'll discuss the Ford-Fulkerson algorithm complexity and more precisely the worst case scenario. If you use DFS, depth first search, the runtime is big O of E times F, right? Where E is the number of edges and F is the maximum flow in the graph. Obviously if you use a BFS, it becomes the Edmonds-Karp algorithm, which runs in VE square time. But we won't be talking about that, we'll be talking about this upper bound, right? And usually the example we give to show that this upper bound is reached is this example. And indeed, the first augmenting path can be A, B, C, D, when you get in that situation. And then a second augmenting path could be A, C, B, D, right? You can go from C to B because there was some flow from B to C, so now you can go from C to B. And so that second augmenting path could be A, C, B, D, and then you would have 1 over 1,000 here, 1 over 1,000 here, 1 over 1,000 here, 1 over 1,000 here, and 0 over 1 here. And then you can sort of go back and forth between A, B, C, D, A, C, B, D, and every time the augmenting path, you just push 1 unit of flow through the graph. So you end up doing 2,000 here, DFS. So the complexity is actually reached, it's E times F, right? The only problem is with this example is if in your DFS when you iterate through the neighbors of A, B comes first, then okay, the first iteration would do A, B, C, D, but then the second iteration wouldn't do A, C, B, D, right? In the second iteration, when you do a DFS, you do A, B, D, right? Because B is the first neighbor and it comes before C, and the only reason why you would go to C before B would be if AB was 1,000 over 1,000. So that's kind of the little problem I would have with this example, and more precisely, so that's the graph we just discussed. I just put the billion instead of 1,000, but theoretically we could, have an algorithm that takes minutes to run because E times F is too big, but because in the Ford-Fulkerson algorithm, right, which is basically do the DFS as long as you find augmenting path. You didn't find an augmenting path break. You found one, add to top flow and go again. Right, so that's Ford-Fulkerson, right? And in the code of DFS, I won't talk too much about it, but what's important is when you iterate through the neighbors of a node, right, you don't change the order in between DFSs, right? So that example only works if you consider there's a sort of bad actor that can decide what's the order of neighbors you explore. And the goal today is we'll try and make an example where we don't have to make this assumption that a bad actor could decide what's the order when we traverse the neighbors, when we iterate over the neighbors. And to make this example, we'll go over the whiteboard because it will be slightly easier to explain. And I will start with an object that's very similar to what we just saw. So here, the source is here, the sink is here, and I'll just put unit capacitors everywhere. And as we saw, right, the first augmenting path could be that one, and the second one could be that one, right? And we would have 2 augmenting paths in total, so 2 DFS, so the complexity would be of 2 times E but here 2 is the total flow. So here we are in f times e, right? And the goal is to scale this graph such that we always reach f times e without having too many nodes, right? We want to have limited amount of nodes, very small graphs when we just consider the number of nodes and edges, but still Ford-Fulkerson takes a long time. And the idea is to replace that center edge with a copy of the graph we have, right? So that may sound weird, but it will look like something like this. So that's the graph we had, and I'm saying we replace this edge by this graph. So instead of having this edge, we'll have a copy of the graph. And that's our new sort of middle edge. And on top of that, we change the capacities of our old graph by multiplying them by 2, and the new graph, the capacities will be 1. And so here we can try and see how many iterations, how many augmenting paths we could find, and we'll make it so that the order of the neighbors will always favor going through the center, right? We order however we want when we iterate through the neighbor. It's just we can't change from one DFS to the other, right? That's basically the name of the game here. And so basically, maybe I'll give names A, B, C, D. Our first augmenting path would look something like S, A, B, C, D, sync. So then the capacities would have 0 over 1, here would be 1 over 1, 1 over 1, 1 over 1, 1 over 2. And then we have a second iteration. Sorry, that's not 0 over 1, that's 1 over 2. And in the second iteration, again, now that I've said that after S the priority is to A, I can't go to D, right? That's really what we're trying to achieve here. So we'll have S, A, we can't go to B, so we'll have to C. And then we can go to B because B to C has some flow. Then B to D, and D to sync. And then we'll have 2 over 2, 1 over 1, back to 0 over 1, 1 over 1, 2 over 2. And now, and only now, can we go to D after S, when we traverse the neighbors of S in our DFS, because SA is full. And so, sorry, the augmenting path would look like as D, and we order the neighbors such that the first neighbors of D will be B and C instead of going directly to the sync. And so we could have something like this: DB, BC, CA, A sync. 2, this goes back to 0 over 1, this goes back to 1 over 1, this goes back to 0 over 1, and this goes to 1 over 2. And the last augmenting path would be SD, DC, we can go to B because it's 1 over 1 currently, CB, BA, async. Alright, so in total we have 4 DFS that were carried out, and every time we go through this middle edge which has unit capacity. So we have again big O of F times E complexity. And now the idea is we'll do the exact same thing. We'll take this graph, we'll copy it, and instead of this middle edge, we'll add a copy of this initial graph. And so it will look like something like this. S, A, sync, D, and then we have what we had, B, C, and instead of that middle edge we have the copy of our small unit graph. And this is our new middle edge. And we said also we double all the capacities we had. So we'll have something like 0 over 4, 0 over 4, 0 over 4, 0 over 4, and here we'll have 0 over 2, 0 over 2, 0 over 2, 0 over 2, and in the middle our building block always appears with unit capacities. And again, we order the neighbor's orders when we traverse or iterate over when we iterate over the neighbors of a node. We always prioritize going to the middle, but we don't change the priority in between the DFS, right? And we'll have something like 4 of them going that way, and all of them will take this middle edge, and then 4 of them going that way, and we'll go back up because those will be 2 over 2 and those will be 2 over 2, and we'll always again use that middle edge, right? And so in total we'll have something like a DFS big O of f times e. And so just to illustrate, the first augmenting path would look like this, and the second one could look like this, etc., etc., etc. Now the idea is to try and learn from that pattern. Every time we recursively create a new graph, how many nodes do we add? We add 2 nodes. How many edges do we add? We add 4 edges, because we add 5 and we remove 1, right? We remove this one and we add those 5 ones. So we add 2 nodes, we add 4 edges, right? So like V like plus equal 2, E plus equal 4, and the maximum flow though is not a plus equal, right? It's times equal to. It's multiplied by 2. So if you do this enough, like if you do this 10 times, you'll have maybe 2 times 10 extra vertices, 4 times 10 extra edges, and 2 to the power of 10 extra flow. And you can see this will blow up even for quite small number of vertices, and this is how we can actually reach this complexity big of f times e and make it so that our code will run for hours, even though the graph is small, right? There's less than 100 vertices, so it's like a very small graph, but our code is a disaster, right? And this is what I wanted to show, because in this example, there's no way to have this with a code that doesn't take out, right? So if we go through the code, and maybe we'll say after this, right, we'll say I found an augmenting path, exclamation mark. Right, if we run this code on the Wikipedia graph, I'm expecting, as I said, 4 augmenting paths, right? 4 iterations through the DFS. And no matter how big the weights are, I won't have a lot better than that. And I'm basically looking for a graph that's quite small in number of vertices, but where I have millions of those lines being printed. So let's try and make this evil graph. And we'll call this make evil graph, and we'll give it an input, which is the number, an integer, sorry, which will represent, right, which sort of steps we are, right? This is the first step, this is the second step, third step, right? Every time we replace a middle edge with our building block, right, we consider this to be the next step. And so we have to think about how we can make this, right? Initially, right, we need to create this building block. So I'll call this initial graph. So this is a dictionary. Each node has another dictionary, and in this dictionary there's a tuple because I want to store the current flow going through the edge and the capacity. Right, and then we can just basically copy what we had here. And we'll have unit edges, right? We said initially we have unit edges. And I said I would use integers for the nodes labels. So let's change this. And so that's our initial building block. In our building block, we also want to point out who is the middle edge, right? Which edge is the middle edge? So the middle edge will be a tuple, right? And it will be the edge from 1 to 2. And if we want the third iteration, then we have to replace that middle edge with this building block 3 times. Actually, if we want the third iteration, we have to replace it twice. So that'll be n minus 1. The first thing we'll do will be to remove the middle edge. So we'll do something like uv equals middle edge, and del initial graph u v del initial graph v u. Then, before adding the capacity, we said we have to multiply all the former capacitors by 2. So before adding the building block, we multiply all capacitors by 2. So that's pretty trivial. And then we want to add the new nodes. So add new nodes so that the middle edge ends up being replaced by our unit building block. And so we have to create, if you remember well, we have to remove this and instead add 2 nodes. Right? We remove the edge and we add 2 nodes. This node is this one, and this one is this one, so we don't have to add those. So we have new node, which will be the length of the graph, and new node 2, which will be new node plus 1, because we label our nodes with integers here. And we want the old source of the middle edge, right? This is the middle edge, this is the source, and this is the destination. And we want the old source to go to have 2 neighbors, right? And those new nodes, right? And so I'll have something like initial graph u being the old source of the middle edge. Let's define here. We want it to be linked to new node and new node 2. With unique capacitors. We also obviously don't want to lose all the previous edges it had. And here I'm kind of using something Python offers here, which is when we iterate through a dictionary, the orders of insertions are conserved, and I want, when we iterate through this node, I want to go to the middle in priority, right? So this is why I first add those new nodes and then I add the rest. Basically, I want this to have priority over those edges. Then we have to deal with this one, and this one, right? This one has 3 neighbors, u, new node 2, and v. So this is a new key in the graph. New node 2, U, and V. And you can notice I put the priority here to new node 2, right? Because I want this edge to be the absolute priority, right? Because this one, I want all the augmenting paths to go through that one. Now I'm looking at this node, and similarly has 3 neighbors, so that'll be very, very similar. It has 3 neighbors, new node to 0, right? Because it goes from new node to new node 2. So when I'm in new node 2, it's just potential edge that only have a capacity, residual capacity of non-null if this one is filled, right? 0 for U and 1 for V. Yeah, all good. And finally, I want to handle C, right? So initial graph V equals, it's linked to those two, so new node and new node 2, but the edges are going that way. So it's going to be 0, 0, new node 0, new node 2. And also I want to keep the former edges you had, right? Similar to U, I'm going to all this to initial graph V. And then I want my middle edge variable to be updated so that I can know in the next iteration which edge I should remove, etc, etc. Right, so the new middle edge is now new node 2. And I want to return this initial graph. So hopefully I haven't made a mistake, and if I just run length of make evil graph 1, I'll have 4, right? I'll have 4 nodes here. Level 2, level 2, I should have 6 nodes, so there's a mistake somewhere. Oh yeah, no, this is not n-1. Yeah, so level 2, I want to go once in this loop, range 1, 2, I'll just go once, and this variable will be once. All right, so that was a mistake, sorry. Whoa. And so, length 2 is 6, length 1 is 4, length 3 is going to be 8, which is in accordance with what we said, 1, 2, 3, 4, 5, 6, 7, 8. And what's interesting now is how many times do I find augmenting path with those graphs. So at the level 1, I'll have 2 augmenting paths, which is what we had said earlier, right? Which is normal. Max flow is 2 augmenting paths. Level 2, max flow is 4, I should have 4 augmenting paths. Max flow is 4, and I have 1, 2, 3, 4 augmenting paths. Level 3, I'm expecting 8 augmenting paths for length of 8 nodes. So I'm having 8 augmenting paths and a length of 8. I'll make this prettier now. Length, not length, number of nodes. Max flow. Right, so now just a bit better. So now if I go to 4, we haven't drawn 4, but we have 16 augmenting paths and only 10 nodes. And if I go to level 5, 2 to the power 5 is is 32. Is that true? Yeah, it is. And I have loads of augmenting path, right? I have 32 augmenting path and only 12 nodes, right? So I'll remove this print. And maybe if I go to 15, right, I only have 32 nodes, but already I'm taking 400 milliseconds. If I go to length 25, now already my program takes a long time. I should have 2 to the power of 25 iterations. Which is this big number, right? And so this will probably take a few minutes. Because the complexity is the max flow times the number of edges. So the actual complexity will be 2 to the power of 25 times the number of edges. But the number of edges is not that big. It's probably like 100 or something. So we'll let it run and we'll see how long it takes. But we've basically successfully made a really small graph that crashes Ford-Fulkerson and basically shows that we really need Edmonds carp when the capacitor is really big and the graph is quite small. I say really need, but actually no, it's very hard to make such an example. So in practice, I really doubt that would happen.